Hello, everyone. Now let's pick up where we left off. Okay, so last time we were talking about low energy absorption, energy emission, these energy states, and these quantum states. So now let's talk about the terms low energy and high energy. So when we talk about low energy and high energy, we are talking about stability. Um, not in terms of the amount of energy. Okay, so it's all relative. Okay, so a lower energy state is you get deeper into the that kind of energy hierarchy that we saw earlier. Okay, an electron in a lower energy state, we say it's in a more stable state. So that means it has it's basically more stable. It's more stable. So we say, okay, this electron compared to the other states, it's in a more stable state and not a relatively speaking, um, um, its position in the atom is lower, okay, or more stable level, okay. So we say low energy means deeper in the well and closer to the nucleus, and high energy means higher in the well and further away. So we could think of these terms as in ways of relativity and distance from the nucleus. Okay. So some substances they will emit light when electrons move between energy levels, right? And we kind of see this. And when matter emits light, like certain materials emit certain colors of light, so all that has a basis in the real world. Okay, so we went over some terms before, but when the electron is in the lowest energy orbital, we call that the ground state. Okay, but electrons are not stationary, right? They're mobile and can move from a different electron energy level or an orbital. We'll talk more about orbitals later on. Okay. So, but when an electron moves to a higher energy level, the atom we say is in an excited state. So it has moved to a less stable state of higher energy. So this is what we call excitation. And when it goes back to the lower energy state, that's called relaxation, or relaxation. Okay. But we describe these kind of transfer between energy states as transitions. Okay, so we could call this like electronic transitions because electrons are moving between two different energy states in, say, the hydrogen atom. Okay. All right. So now let's relate this back to the experiment we saw, where we saw a light source emitting in light spectra with different colors of light, different color bands of light in the spectrum. Okay, so pretty much the electricity applied across the lamp for hydrogen and other lamps. That we saw the spectra for, okay, it provides enough energy to excite the electrons from the ground state to the excited state. So remember, like how we saw that if we visualize the two quantum states, we can do that by providing energy or radiation of enough frequency or energy to the quantum system. In this case, our electron. Okay. So they promote from the ground state to the excited state. So let's answer some of these questions based on the process we saw and know so far. So for an electron to move from the ground state to a higher energy excited state, would the electron have to absorb or would it release energy? Let's explain our answer. Okay. So if we think about electrons in a lower energy state, that means they are lesser energy. So they only have energy to stay in that energy state. They can't move up, right? Unless they get more energy and can break free from the attractive force from the nucleus. So we can say something like, to reach a higher energy, state. The electron has to gain or absorb. Okay, so it has to gain or absorb energy to make the transition. To a higher energy level. Okay, so now let's go to the next one. If an excited state atom wants to return to the ground state, would that be an electron absorbing energy or would it have to release energy? So it's kind of the opposite of the previous question. So if we have an electron in a higher energy state, okay, but wants to return to the ground state, which we know is the lowest possible energy state for an electron to occupy, we'll probably have to get rid of all that energy so it can fall back down to the original of the ground state, okay? So in order to go back down to the grounds to a lower energy state, the electron will have to release energy. Okay? All right. Now let's look at this next one. For an H lamp, are the lines of light seen caused by energy being released or absorbed by the hydrogen atoms in the lamp? How do you know? Okay. So remember, when we absorb light, the energy is now being consumed to promote the electron to a different energy level. Now, remember, energies that we learned in the last chapter that energy is conserved. So, in order for the energy to, in order for the light to be seen, the electron must release that same amount of energy in the form of a photon. That, if it's in the visible, if the frequency is in the visible region of light, we can perceive it and see it as a color in the naked eye. Okay. All right. So in this case, we can say the lines of light are being emitted by the lamp. Right, because we look at the lamp, the light goes into the spectroscope, and we see those colors of light in our instrument, right? So, therefore, energy is being released by the hydrogen atoms. Okay, so that's how we know that the light's being emitted. Okay, now let's complete the statement by selecting the better choice. Okay, the light seen in the emission spectrum of hydrogen corresponds to the electron moving from a higher or lower energy orbital. Higher, because we know that to release energy, you must go back to a lower energy level, and then that the energy difference between the two levels is released as a photon of light. So those lines that we see are the result of an energy level, the energy corresponding to a specific transition when the electron goes back to a lower energy state. Okay? So when we're falling back down to our original energy state or lower energy state, that's emission of light, and when we go to the higher energy state, that's absorption of light. So electrons are gaining energy. Okay. Okay. Now let's look at this diagram below. So figure 3-3A shows an excitation of an electron from the 1 to 4 energy level. So the arrow represents the transition of the electron. The energy needed by the electron is provided as a photon with energy equal to the difference in the energy between the n equals 1 and 4 level. Okay? So, like we said before, the electron, due to its attraction to the nucleus, will eventually return to a lower energy state. So, these excited states, they're short-lived, and that's because, naturally speaking, the electron would like to remain close to the nucleus, so that's why it drops back down. Okay. So, remember, for an electron to move back to a lower energy level, it must get rid of the energy to make this transition because energy is conserved. So it releases a photon, and what photon is, we can call a photon a particle of light. So let's say a particle of light. So we'll talk about the particle nature of light in a bit. But this is one example of the particle nature, is that we absorb some light, it provides some energy to make the electron jump to a different energy state, and that has to do with absorbing something of a particle nature. So that can't be like due to waves. It has to absorb something of unique finite energy, and that's usually associated with something of particle nature. Okay? And this photon will have energy equal to the energy difference between the two energy levels. Okay? So we call this relaxation, as I said before. So, how an electron relaxes, it doesn't always have to be in one way. It can be in multiple steps, one way, or multiple transitions. So what's important is that it goes back to an initial and final state. Okay? So you could think about this like going down a flight of stairs, right? You could go down stairs one step at a time, or if you're kind of in a hurry, go down several steps at a time. So it doesn't matter how many steps you go down. Okay? So there are multiple pathways for an electron to relax. So that makes this kind of makes like how we deal about energy transfer in certain reactions, in certain processes. It kind of makes us think about how we can make the most efficient use of what the electron's doing. So it gives us kind of some incentive in the future to kind of develop processes that make use of this, of the nature of the electron. Okay. All right. So, like we said before, the energy of the photon that we absorb, it must be equal to the energy gap between two energy levels. of the transition. So it can be from n equals 1 equals 4. We must absorb enough energy to bridge that gap. Or n equals 1 to 5, 2 to 3, 3 to 4, 6, 5 to 6. So the energy must be equal that amount to promote the electron. Okay? All right. So the energy of the photon absorbed will have a characteristic wavelength and frequency of a finite amount of energy, or a specific amount of energy, like we have been talking about this week. Okay? So what happens here is that we saw this equation before: H equals HV, H equals HC lambda, the value for energy, the equation for energy. So in this case, if we're excited, we're doing an excitation, or the energy level of the final will be greater than the energy level of the initial. Okay? So we call this excitation. Now, that involves absorption of a photon of light. Now, if we emit a photon of light, then the energy state of our final state is going to be less than our initial state. So we start out at a higher energy level. What we end up with is a lower energy level. And we see here that the energy of the photon is always going to be the same here. Change in energy equals n equals 4 minus E n equals 2. Okay, so the energy of the photon is an absolute value. The amount it takes to go bridge between the gaps there is going to be the difference there between n equals 4 minus n equals 2. So in this case, this energy difference would be, so E photon here would equal delta E equals E of the fourth. Okay, let's not write like that. Like that. Okay? So that would be, say we excite from the n equals 1 to the n equals 4 level, and then the electron will relax back down to the n equals 2 level. So say we, let's just say that's our scenario here. Okay. Okay. So in this little tidbit here, we state that in order to make these transitions, the photon must possess enough energy that's equal to the difference between the energy difference between the n equals 1 and 4 level for A, and then for figure B, it must be equal to the energy difference between the n equals 4 and n equals 2 levels. Okay? All right. All right. So usually if the energy of a transition corresponds to a portion of the spectrum in the visible region, we can visualize this light. But if it's in any other kind of region, like the UV vis, UV region, or infrared region, we would need a detector to help us see the lines. So we can't actually detect it with our own eyes. Okay? So these energy differences, if the photon of light is in the visible region, we can actually see the light. And that's kind of what we see now every day, the light, the colors of things. That's due to pretty much the electrons and materials looking, or releasing a photon of light when it gets excited, when light shines on it. So pretty cool. Okay. All right, so now let's go into more, how do we calculate the energy of a line in the hydrogen spectrum? How do we calculate the between energy levels? Okay, so we'll pick this up in the next video here. So I'll see everyone in the next one. Okay.